Okay, hello everyone. Ladies and gentlemen, good afternoon and welcome to today's webinar. My name is Võ Trung Giang, English teacher at Toyo University, and I am delighted to be your moderator for this section. We have an exciting webinar filled with insightful discussions and valuable information that I'm sure will enrich your understanding of pitfalls to avoid while using multi-objective optimization in machine learning. Before we delve into the details, I would like to take a moment to introduce our esteemed speaker today, Junaid Akhtar, PhD in data science in Paderborn University, known for their pioneering work in multi-objective optimization, scientific machine learning, with a career marked by co-founder and CTO of Genie Quantum AI. Kashmir's for AI company, they bring a wealth of knowledge and experience to our virtual stage today. Also, I would like to take a moment to express our gratitude to all of you for joining us from different corners of the world. Your presence here today is truly appreciated. Today's webinar is not just about sharing knowledge, but also fostering a community of learning and collaboration. We encourage you to actively participate by asking questions and engaging in the discussion that will follow each presentation. Your contributions are what make events like this not just informative, but also enriching for everyone involved. Throughout the section, we aim to provide you with actionable insights and perspective from our esteemed panelists, who is experts in multi-objective optimization, scientific machine learning. Their expertise will shed light on key trends, challenges, and opportunities in pitfalls to avoid while using multi-objective optimization in machine learning, equipping you with the knowledge you need to navigate and excel in this dynamic landscape. As we proceed, I encourage you to make the most of this opportunity to learn, to connect with fellow participants, and explore new ideas. Let's engage with curiosity and enthusiasm, keeping in mind that the more we interact, the more we can learn collectively gain from this experience. Without further ado, please join me in welcoming Junaid Akhtar. Sir, we are delighted to have you today, and we eagerly look forward to your enlightening presentation. Please, everyone, join me in giving a warm virtual welcome to PhD Junaid Akhtar. Once again, thank you for being here with us today. Thank you.
Thank you very much for the kind introduction, and I would like to thank everyone who is taking their precious time and joining these webinars. And I would also like to thank you, Core Research Foundation, for organizing this webinar, giving me this invitation. I think these webinars are really important, at least in my personal journey. They have helped a lot. I coming from a very remote part of the world. I would say I come from Kashmir, if you guys know about it. And I had access to this wealth of information after joining many webinars, and right there sitting in Kashmir or other parts of the India, I could listen to speakers from all over the world. So once again, I would like to thank you, all of you, for organizing this and giving me opportunity to talk about my research field, which is multi-objective optimization and machine learning. So I work on both of them. I will go ahead and explain each of them what they mean. But before that, let me try to share my screen. And I would like to ask you, are you able to see my screen, and is it visible enough? Like, is it big enough or is it too small?
It actually is okay if you're looking at a system, but I don't know about the phone or an iPad or a tablet. But it's fine. You can go ahead with this.
We have We have 1 hour, right?
Yes.
Okay. So I can also try to make it better. That's why I was asking you guys. So I think there are some messages too small. Okay. Let's do one thing. Let me just just give me one moment. I will share my screen again, and I would need your kind response. Is it better now?
Yes, it's
Yes,
better.
better.
Okay, perfect. So this is the topic that I'm gonna talk about today, and I will need access to chat. So I will keep that in front of me so that if there are some questions. So first I want to ask if about the audience, if you guys have heard about multi-objective optimization. I'm sure that everybody has heard about machine learning, but I would also like to know if people are aware about what is multi-objective optimization. Have they heard it in other talks, or maybe some people are even doing their research in the field? You can just type in the chat yes or no. I have chat in front of me, so I can quickly take a look and see how I have to proceed. And as was requested in the beginning, if you have any questions, stop me, ask the questions. I think it's important for these webinars to be interactive. I also don't want to feel like I'm talking to a screen, so it's good if you stop me and ask questions whenever you want. So Liberius says, I don't know about it. Okay, we have another no. So I will not take a lot of time on this. So maybe I go ahead and I share with you the contents of the talk. Okay, so this is going to be the contents of the talk. I will give a brief introduction, which will be basically motivation, why we are talking about what we are going to talk about. And then maybe a little bit of formalization of multi-objective optimization. What is it about? And how it can be used in deep learning, or why do we need to use it in deep learning or machine learning in general? And from a personal journey, when I started exploring multi-objective optimization and machine learning, I had I would say I had a bit of a rough journey because there's not a lot of work which has been done in this field. So there is this field called multi-objective optimization, and a lot of people have worked in it. Similarly, as you all know, deep learning is quite an famous field. Almost everybody in computer science and even other disciplines are now familiar with deep learning. But at the intersection of them, there wasn't much work done. In fact, some of the work I found misleading, and then that resulted in my work where I'm talking about if you want to use multi-objective optimization in deep learning or machine learning, there are some things which one has to keep in mind, and I will highlight those things. So this year I'm going to travel back home. So my flight will be from Frankfurt to New Delhi. So giving this example, I want to motivate what multi-objective optimization is. So of course, there will be a lot of options of flights. For example, here I have these three flight options which I can take. The prices and the timelines, they are dummy. So it doesn't take 2.5 hours to go to New Delhi. It takes minimum of 8 hours for a direct flight. But this is just for the sake of showing you guys. So I have, let's say, three options here to travel, right? Some of them are expensive. For example, this is a $200 flight, and some of them are cheap. This is a $70 flight. And the expensive ones, usually they are direct flights, right? You must have experienced this. The more money you pay, the more comfortable flight you get, or the less that it takes the time to reach that place. And this is the cheapest one, and hence we see that it takes the most time. So let me try to plot it. on a two-dimensional plot. So on the x-axis, I will have cost, and on the y-axis, I have time. So this would be the the green point, right? So somewhere around here, we have the cost of $70, and it has 2.5 hours of flight time. And this would be the purple one. It costs around $200 and takes 1 hour time. And this would be the red one, right? So it has $100, about 3 hours of time. So now the question is, which flight do I take? So that will depend on me, right? Or you guys, depending on how rich I am, how much money I want to spend, I will choose one of these flights, right? So I might choose the green one if I want to save money. If I have a lot of money, I will choose the purple one if I want to save time. So this is what is at the core of multi-objective optimization. Sometimes there are more than one solutions, and then we have to choose which solution we want to go with. So there is not a single optimal solution. There are many optimal solutions. Now the question is, what is an optimal solution? So I want to ask you guys a question. So who of you would be fine in taking this flight, the red flight, which is $100 flight and takes 3 hours? Would any of you choose this flight? If no, then why? You could also unmute yourself if you want to, or you can quickly write. So I have one answer, which is no. So obviously I wouldn't choose this flight because the green one here, this flight, is cheaper and takes less time. Exactly. So Carlo has an answer. This is cheaper and it takes less time. So the green one would be an optimal solution. In other words, what we would say is that in multi-objective optimization, the terminology that we use is that the green point here is a non-dominated point. Okay, well, okay, we have an answer that it depends on need. Well, it depends on need if you want to choose from green to purple, of course, if you want to save money or time. But I would doubt that anybody would choose red one or green one, because the green one is better in both. It's cheaper and it's faster than the red one. So if there is an option of choosing green flight, I wouldn't assume anybody would choose the red one. In other words, what we say in multi-objective optimization, we say that the green one is a non-dominated point. So it is a point which is, there is no other solution better than the green one as of now. There could also be a flight, which is here denoted by the black dot. I didn't show it here because it would clutter everything. And if this is an option, then one would also go with this one. So it has the same price as the red one. So it is also a $100 flight, but it takes less time. Okay, so it would be it depends on the need and on your convenience. Which one would you choose from green, black, or purple? But I wouldn't choose red one if I had to choose out of the solution set. So these points, the green, black, and the purple one, would be called non-dominated points in multi-objective optimization. And that's what we are usually after when we are optimizing more than one objectives. Now, what are the objectives here? The objectives are cost and time. And this situation arises everywhere in life. In fact, I would say our life is a multi-objective optimization problem, right? Sometimes we are optimizing our career and fun. For some people, it might be the same thing, but sometimes we are optimizing our personal life and professional life. We want to buy a car which is cheap, but we also want it to be super fast. You know, a lot of things out there are multi-objective in nature. And if you want to, check if a point is non-dominated or dominated, what you can do is you can very easily draw a cone on that point, a cone by perpendicular lines. And if there is no point falling inside the shadow of that cone, for example, here there is no point falling inside, then one could say that that this point is non-dominated, that this is an optimal solution. Okay. Similarly, I can draw a cone here. I can draw a cone here. There is no point in the shadow of any of these cones, so they are all optimal solutions. However, if I draw a cone here at the red point, we see that the green one and the black one fall inside its shadow. right? So this red one is not an optimal solution, as we already discussed, right? That we wouldn't want to take the red flight. Now, this is a real life example of multi-objective optimization. When we go to deep learning, for example, or machine learning, there are also cases where multi-objective optimization might arise, right? Because using machine learning and deep learning, what we ultimately want to do is we want to solve real life problems. That's the goal, right? So how many of you have heard about MNIST dataset or CIFAR dataset? I think it's quite common in the machine learning community by now. These used to be the standard tests for a long time, right? So MNIST dataset is a dataset where we have these handwritten digits from 0 to 9. And using different machine learning techniques, the job would be to identify what a number is. So if I show my machine learning model, hey, here is the number 9, it should be able to recognize that this is number 9, right? So this would be the MNIST dataset. And then the CIFAR dataset has images of objects around us, images of animals and cars, etc., etc. Doing these two tasks individually. So if I train a model on CIFAR dataset, I think it's quite easy to train a model on CIFAR dataset, and then it will be able to recognize a car which you never showed it to you, to the model, right? Similarly, if you have MNIST dataset, it will do the job. But here I have a special dataset, which is called CIFAR 10 MNIST dataset, which is the superposition of the numbers and images. Okay, so we have the numbers from 0 to 9, and then there are images. For example, here we have an image of a horse. I don't even know what is here. I think it's 8 superimposed with a truck. And then the model has to learn the features of both data sets, right? It has to learn the features of how numbers look like, and it has to also learn what are these images that are being fed to the model. So this inherently becomes a multi-objective task, right? Because there's a conflict between these two tasks. Like the earlier case, there was a conflict between the cost and the time of the flight. So the conflict part is the very important thing in multi-objective optimization. So if you have a conflict, you cannot use single objective optimization to solve your problem, because you have to optimize more than one objectives first of all, and then they are conflicting. There is always this, that if you optimize one, the other gets worse, right? If you're optimizing cost, the time gets worse. If you're optimizing time, the cost gets worse. Okay, now let's formalize it a little bit. So formalizing it would mean that we have to write some mathematical definitions. So here we have M objectives. And in multi-objective optimization, the goal would be to optimize all of them simultaneously, right? Where L, these are the objective functions, so our loss functions in machine learning terminology. And here we have M loss functions. So normally, people who have been already using machine learning, what we have is a single loss function, right? And then we use gradient descent, back propagation or whatnot to optimize that loss, optimize the parameters, right? To minimize the loss function. And theta here would be called in multi-objective optimization decision vector or model parameters. So these are, for example, the parameters of, let's say, if you are doing regression, would be the weights and biases, or if you have a neural network, the parameters of the neural network, right? And the goal is to jointly minimize all of these objectives or maximize. But the important thing is that all these objectives are conflicting in nature, and we want to optimize them simultaneously. Okay. And yeah, one could also write it in this fashion here. So I put the whole vector in just one bold terminology. So L here includes all of these L1, L2, and LM. This is just formalizing the stuff. That the basic idea is that we have more than one objectives which we want to optimize at the same time. Now, you might have seen pictures like this here in usual machine learning stuff, where we have this landscape, right? We have this lost landscape, and our goal is to get the minima of the landscape. For example, take this orange one, forget about the blue one. Using gradient descent, what we would want to achieve is we would like to go to the minima of this landscape, right? Lost landscape here. But when you have two objectives and they are conflicting in nature, then you don't have a single optimal solution. What we instead have is something called a Pareto set. So we have a set of solutions like this when we had this flight example, we had a set of flights, right? We had many options and we could choose one of those options. So that those solutions, if you put them in a set, curly brackets, that would we call a Pareto set. And corresponding to a Pareto set is the Pareto front. So this is in the objective space. When you plot the objectives, this is plotting, these are the parameters of the model, and these are the objectives itself. So here we have something called a Pareto front, okay? Just for visual representation. Now we already know that there are a lot of methods in single objective optimization. As I was mentioning, there is, for example, Adam optimizer, there is stochastic gradient descent, momentum-based methods, etc., etc. There are many methods to optimize a single objective optimization. Similarly, people have come up with optimizing multi-objective optimization. The single, as I was saying, single objective optimization will not work out of the box if you want to use it on a multi-objective optimization, because it doesn't take into account that there is conflict between the objectives. Okay. One of the methods which is out there is weighted sum method. So what you do is you turn a family of multi-objective problems into a single objective optimization problem. So if I have these M objectives, L1, L2, L3, Lm, what I do is I sum them, all of them up with a weighing factor alpha, and there's a condition on alpha that it should sum up to 1. Then it becomes a single objective problem. And then I can use all the single objective optimization methods which already exist out there in the machine learning community and optimize this loss function. And every time I choose a different alpha, I discover a different point on the Pareto front. Okay, so here is the Pareto front, for example, in this image between L1 and L2. Which we call objective space. So this is a Pareto front, which consists of the non-dominated points, which we discussed in the beginning, right? But a Pareto front could also look like this here in the second image, right here. So it might have a concave, non-convex part and also a convex part. So the non-convex part is denoted here by red. Or it might be fully non-convex. So this one is convex. Then we have a Pareto front which has convex and non-convex part, or it might be only non-convex. Now, on the one hand, this weighted sum method is very easy because you just need to sum up the objectives. Of course, you have to choose alpha. So that's one free parameter there. But on the other hand, it has some limitations. The limitations is that by theory, it's not able to find the points where it's non-convex. If your Pareto front inherently looks like this, if it's convex, then it will be able to find all the points on that Pareto front. But if it has non-convexity inside it, then it's not possible to find it via weighted sum method. There's another method which is called the multi-objective gradient descent algorithm, which is the steep-end descent method version, but in multi-objective optimization setting. So we already know the gradient descent method, right? We do it in single objective optimization. Similarly, people have written down, they have there's a whole foundation and theory behind multi-objective gradient descent algorithm. If you want to go deeper into it, please let me know. I can share some resources. And here the goal is we need to find a common descent direction and a step length, right? We need to find the step size and the descent direction such that all the objectives are getting minimized simultaneously, okay? And this is, I would say, this has a very strong mathematical foundation, and the convergences and everything is guaranteed. However, a little bit challenging to implement. And then we have one of the most famous multi-objective optimization methods out there. If you just Google multi-objective optimization, what you're gonna maybe see is something like NSGA2 and a picture like this. So this method is inspired by biology. So basically what you have is you have a generation of models, and then what you do is you do something called mutations and recombination. You create new offsprings, and then you do sorting. So it's called non-dominating sorted genetic algorithm, and there are first version, second version, and third version of it. But it's inspired by biology. However, not suitable for deep learning for the reasons which I will explain later. So the first two methods here are gradient based, right? There we involve one way or the other way gradient descent. So we are taking gradients of the objective functions with respect to the parameters of the model, right? And this one is genetic based, so there are no gradients involved here. And this would be one of the reasons why it's not suitable for deep learning, where we do need to take gradients. So I would take a pause here for questions, and then I will maybe go ahead with the rest of the slides. Do we have any questions or comments, suggestions? I think it's very important to get the motivation correct. I think if you just are motivated enough to know about multi-objective optimization and see somehow in your day-to-day research where you can apply it, then I would consider this as a successful talk. So I really appreciate if you would ask any questions you would have in mind. Yeah, I think Liberius, I'm sorry if I'm not pronouncing your name correctly. You can use multi-objective optimization method anywhere where you have conflicting objectives. Yeah, that's the important point. So if the objectives are not conflicting, I will show some results in some time, then it doesn't make sense to use all this methodology. You can use a single objective optimization. For example, you might be optimizing two objectives. You might have two objectives, but they might not be conflicting at all. So if you are looking for a cheap flight and also a flight which takes the longest time, right? So they're not conflicting. A cheap flight is usually automatically taking the longest time. Then it wouldn't make sense to use multi-objective optimization. So if you have NLP, whatever you have, it's actually multi-objective optimization is independent of deep learning. The field exists independent of deep learning, and it's quite old. So if you have cases in NLP where you have some sort of loss functions which are conflicting with each other, yes, you can use multi-objective optimization. Yes, conflicting objectives is very important. Okay, let's go ahead and talk about this one, about deep learning. So as I gave one example, about this image dataset, right? So we had this Cypher 10 MNIST dataset where we had, let me show it again, this one, where we have these basically numbers superimposed with the images of whatever. So this is a deep learning problem, right? Because you would use maybe convolution neural networks to study this problem. Now, so in deep learning itself, there is a lot of problems inherently which are multi-objective in nature, right? And one of the examples is when you try to include domain knowledge while you are learning from data. So I would ask here, how many of you have heard about physics-informed machine learning or physics-informed neural networks? Has anybody heard about them? No? Okay, I will go ahead and explain it. So normally what happens in machine learning or deep learning is it's a data-driven learning, right? So you have a lot of data, and what you're going to do is you have a model, you train the on that data set, you split maybe the data set in the training data set and the validation data set and whatnot, right? But it is essentially learning from data. And what happens is oftentimes getting this data is very expensive. For example, there might be medical data which we might need, and it's very scarce, right? So there are some diseases which exist out there which are not so common. So naturally we don't have data, or we might not have data about some expensive physical phenomena, a physics system which is very expensive to simulate, right? It might take a lot of money to get the actual data from the system. And that's where the physics-informed machine learning comes into play, which says that if you know some physics about the system, now what does it mean to know about physics about the system? I will explain in a moment. But the idea is that we don't just learn from data. If we know something about the system itself, like we have some knowledge about the system, where did this data come from? For example, if I have data from weather, and I know some equations of the weather data, what I do is I can encode these equations in a way that I tell my neural network that this is the physics of the system. So what it does is it makes the neural network informed about the system. So I don't need a lot of data to train my system because it's aware about some of the physics which exists in the system where from the data is coming. Okay, and this has become a very, very popular and interesting field called physics-informed neural networks, or physics-informed machine learning in general. So here what you see is on the right-hand side, I have a neural network, and using a neural network, you can encode the inside a neural network, you can encode the physics of the system, or what you can also do is you can use this neural network to solve differential equations. So on the left-hand side, I have some differential equations. So this n represents an operator in a differential equation. Could be simply, for example, du by dx, or it could be du by dt. You know, everything around us, if you model it, if you want to mathematically model it, turns out to be a differential equation. Almost everything. Even the simplest Newton's laws, it's a differential equation. If you go to economics, there are a lot of differential equations. You know, a gradient descent itself, it's taking a derivative, right? So it does involve a derivative. Everything we try to model in our day-to-day life, we end up in a differential equation. And the idea in physics-informed neural networks is that what we can do is we can combine the learning from the data and from the physics. Now, what is this learning from the physics? It is the learning that we already know the differential equation of the system. For example, I was giving example of the weather data. So if I have a data from weather, and I also know equations of the weather, at least to some extent. So I can encode these equations in my neural network. Now, why is that possible to encode these equations in neural network is because in a differential equation, we have derivatives, right? We will have, let's say, first derivative in x, second derivative in x, while x is the input, right? X is the domain of the differential equation, or we could also have time derivatives. And we know that it's very easy in a neural network to take these derivatives. Here, for example, del over del t, del over del x, or the second order derivatives. We can do all of this because of backpropagation. And using this, it's possible to encode physics inside your model, inside your neural network. Hence, by adding physics to data learning, it becomes very efficient. It becomes easier for the network to learn from the data. Okay, and what people normally do is they would just add these two loss terms. So you have a loss term from data, which would be the supervised loss, and then you have a loss term from physics. Okay, now how to actually calculate this loss function, I did not explain it here, and I think it's not so important. But the point is that one can calculate this loss function, and what people normally do is they just add these loss functions together. But it's not clear what should be these weights, what should be alpha data, how much emphasis you should put on the data, and how much emphasis you should put on the physics. So there is no problem in adding these two loss functions as long as they are not conflicting, right? We're talking about conflicting objectives. Another point is that how do we choose this alpha data and alpha physics? Who is going to choose them? So usually what people do is they do a lot of hit and trial, and they find a good combination of alpha data and alpha physics. And what we did is, or what people have already tried to do is that they treat this as a multi-objective problem. They say, okay, this L data, which is one loss, and L physics is another loss. They inherently could be conflicting if, for example, you have noise in the data. So I know the physics of the data via these differential equations, and I have data from the system, but I might have done some mistakes while I'm taking the data from the system. The sensors might not be working perfectly while I'm taking the weather data, or one of the sensors might be damaged. So there could be noise inside the data. And what it means is that these two objectives are inherently conflicting. So this is what the field of physics-informed neural networks or physics-informed machine learning is in principle. So this is like a very broad perspective of physics-informed machine learning. And I would highly recommend that to take at least a look at this field, because it's getting highly popular, and there's a need of such of a field, because as you might have heard, we have now these big models, right? We have large language models, and they have like billions, trillions of parameters, and they are getting bigger and bigger. And one way to compress your models, to reduce the number of parameters in your models, is if you know some physics about the system. And once you know that physics, you can encode it in your neural network, and you wouldn't need a huge model, or you wouldn't need tons of parameters. You wouldn't even need tons of data to learn. Okay, so this field is very important. Now I have some examples here. So this is one of the equations which we use to simulate the data. It's a logistic equation. It's not even a partial differential equation. It's an ordinary differential equation, a very simple system. Let me go back. Yeah. So and we already know the exact solution. So now why we choose an equation where we know the exact solution is because we can create labels, right? So my input would be t. This is what goes into the neural network, and then I already have the exact solution, so I can create the losses, right? And then I already know the physics of the system because I know the equation, right? And this I can encode as a physics loss in my system. And here are two plots where on the left-hand side, we are learning from data, and on the right-hand side, we are learning from physics. Okay, by learning from physics is we are solving the differential equation using neural networks. We are not using the exact solution. While on the left-hand side, I'm using the data which I created from exact solution to learn the solution of the system. Please ask questions if you have any. I think it's very important. Now, in these plots, what I'm showing is on the left-hand side, I'm learning from data, but now this data has some noise. In the previous plot, there was no noise in the data. Now I have noise in my data. So naturally, what the model learns is it overfits to the noise. You see, it doesn't care about the original system. The original system is this blue dotted line, right, where from the data came. But while we were recording the data, we added some noise to the system, and our model fits to the noise rather than to the original system because it doesn't care what the original system is. However, if you look at the plot on the right, I added some physics to the system, 0.1 physics, which means I choose the coefficient of the physics loss as 0.1. Alpha physics equal to 0.1 in, let me go to the equation to just make the point clear. So in this slide here, I choose alpha physics as 0.1 to add some physics to the system, to add some physics information to the system. And as you can see, it fits, it respects the original solution, right? Just by adding a little bit of a physics to the system, I'm getting closer to the original system. So this is the power of physics-informed machine learning, that if you know some physics about the system, you can basically avoid overfitting. You are not overfitting to the noise. Okay, now I would like to comment on some of the pitfalls that one should avoid. I hope you are motivated enough to use multi-objective optimization in your work, or you at least see the potential. And I choose physics-informed machine learning because I find it very interesting, but it can be anything. It doesn't have to be physics-informed neural networks. You don't have to care about it. It's an interesting field. That's also a reason I wanted to introduce it. But wherever you see conflicting objectives, the study is valid and you can use it there. But before moving ahead to the final part, which is pitfalls to avoid, if you now have decided to use multi-objective optimization, I would like to take maybe some questions or comments. No? Okay. So let me then go ahead. So here's one of the plots that I, when I was trying to learn about multi-objective optimization. And here we have data loss on the x-axis, physics loss on the y-axis. It doesn't matter. Could be anything. Something on x-axis, cost on the x-axis, and time on the y-axis. But this is an actual plot from an actual research, a published research. And what was the first thing which I noticed in this plot was about the Pareto friend. So in the plot, it said, if you look at the research, here is the link. It said that the green part here is the Pareto front of between the physics loss and the data loss. Now, I would like to ask you, based on our discussion, would you qualify this line as a Pareto front? If you remember the discussion about the dominated and the non-dominated points, where we draw these cones, right? So if you draw a cone here at this point, here, if you draw a cone here, you will see that these 2 points fall inside this cone. So this point here is not a non-dominated point, because these 2 points are better than this point. It's like this red flight, which we would not take, right? So it's not an optimal solution. So it's important to understand what Pareto front means and what an optimal solution means, because if you're not even able to recognize what a Pareto front is, then we're in a huge problem, right? Because let's say I have an industry problem where we are optimizing cars or whatnot, and then I have to make a decision based on the Pareto front, right? Somebody has to make a decision. How efficient do we want to make this car and how expensive it has to be? And if we have the wrong Pareto front in the first place, if we have identified the wrong Pareto front, then it's the decision is obviously going to be wrong itself, right? So again, I show this picture here that if you want to see what a Pareto front looks like, just draw a cone, and only those parts of this objective space belong to the Pareto front where there are no points inside the shadow of this cone. Here it would be the green part. So the point here would not be a point belonging to the Pareto front, because when you draw a cone here, then this part, this whole part here lies inside this cone. Okay, so this is the first mistake which people tend to do in identifying the Pareto front. Now, the second one is that multi-objective optimization is only useful when objectives are conflicting. We already discussed it, and there was also a question about it. But here I want to show you some plots which we created based on our study on physics-informed machine learning. So on x-axis, we have the data loss, and on y-axis, we have the physics loss. And what we are doing is we're adding some noise to the data, right? And that's signified by these colored bars here. So from left to right, where the noise addition is increasing. So when we have no noise in the system, which is this purple bar here, means this point, then the Pareto front doesn't exist. Or in other words, the Pareto front is just a point. Why is that the case? Is because there is no conflict between the objectives. However, when you increase the noise, let's say you go to the blue bar now, which has standard deviation of 0.1, and then you see there is some conflict. So there is a Pareto front which exists. And as you keep increasing the noise, then you see that the Pareto front goes more and more away from the origin. So it's very important to use multi-objective optimization only in a setting where you have conflicting objectives. And in this point, I want to emphasize on the scaling of this is a very minor point, but I myself got a bit confused when I looked at the plots from the research of other people. So it really depends how you plot your Pareto front. If you're using a linear scale while you are plotting them, which is on the left-hand side, or you're using a logarithmic scale, which is the case on the right-hand side. As you can see, they are the same. So it's the same data, same Pareto front. On the left-hand side, I'm plotting it on a linear scale. And on the right-hand side, I'm plotting it on the logarithmic scale. Now, what has happened here? What has happened is that on the left-hand side, the shape is convex. And on the right-hand side, the shape is non-convex. So it's trivial because I changed the scale. But what I have noticed is people try to attest some explanation to this. And in multi-objective optimization, it does have explanation. So if you have a convex front or a non-convex front, it says something about the nature of objectives. Okay. However, what I saw is that people tend to ignore this detail and they go ahead and start explaining, hey, this front is non-convex, and it's because our underlying problem is, for example, has this and this parameters. So all kinds of explanations which they can give. However, it's very simple to see that it's only because we plotted them on a different scale. So this is something to keep in mind before going further in explaining your observation. It's important to have a look why we are getting what we are getting. I think this is a general comment in science. Whenever we get a plot, it should one should really analyze it and have a careful look of why we are getting what we are getting before explaining it further. So again, it was the same plot here, which I showed earlier. You can see that the scales here are logarithmic, right? And hence they have this non-convex front. But in principle, this front is not non-convex. It's a convex front if you plot it on a linear scale. And in this paper, there was a lot of explanation given why this front is non-convex. Okay. Another important point is when you want to use a multi-objective optimization. Now, I gave you at least 3 different methods: weighted sum, objective gradient descent algorithm, and evolutionary-based algorithm, right? Which was this NSGA2. However, I didn't get a question, which one should I use, right? Because there are 3 different methods. So which one should one prefer? This would be one question. And another question would be, what should you expect from a method? I think this is one of the most important things which is lacking in machine learning research in general, but specifically in multi-objective optimization. So people tend to go online and use models which people have already used, or maybe sometimes write their own models, but don't really understand the theory behind the optimization method. And this can prove fatal sometimes, because one has to know what to expect from an optimization method. One has to know the theory behind an optimization method, right? So for example, if I'm using weighted sum, which is one of the methods I discussed, and I explained that it's not possible using weighted sum to discover the red parts of a Pareto friend. For example, here I have a red part of the Pareto friend, which is a non-convex part. It's just by theory, weighted sum is not capable to discover this part of the Pareto friend. Similarly, if the front looks like this, the weighted sum will fail. It will not be able to find this part of the Pareto friend. So if I go ahead and expect my weighted sum to find all the Pareto friend, it would be a mistake. And let me go back to the plot, which I just showed. So in this plot, for example, the front is non-convex, right? And the method used here was weighted sum. The method used by the authors is weighted sum. So if I already understood what to expect from weighted sum and I got a non-convex front, I would be very skeptical, because I know that weighted sum should not be able to find non-convex parts of the Pareto friend. So this is very important to keep in mind what optimization methods we are using and what to expect from them. Okay, now this is a Pareto friend, same problem which I showed before, the logistic equation, but using the MGDA method, which is the multi-objective gradient descent algorithm. We just wanted to make sure that the fronts that we are getting are really convex. Okay, so it's important to maybe verify your results with one more method. And then, of course, as I mentioned, that the NSGA second, which is the evolutionary algorithm, which is used in multi-objective optimization a lot, it's kind of become the benchmark. So we wanted to do a comparison, which method performs the best. And we can see that the weighted sum and the MGDA almost do the same job. So here in the light blue and blue are the weighted sum and MGDA, while as the NSGA2 doesn't do as good of a job compared to these two in finding the Pareto friend. And the real problem with NSGA2 or any evolutionary algorithm is that they are not scalable. What it means is that if your models become bigger and bigger, which is the case in neural networks, for example, large language models, they're really huge. They have a huge number of parameters. In fact, most of the models that we use in Gen AI are really big. So NSGA2 is not suitable for the following reasons. So here is a plot where I'm increasing the size of the network. So 19991 means that I have 1 neuron in my first layer and 1 neuron in my output layer, and I have 3 hidden layers which have 9 neurons each. And then I increase the number of neurons on each of these layers. And you can see that as we increase the number of neurons, the performance decreases drastically, making NSGA2 not suitable for using with neural networks. It's not a gradient-based method, so I would anyway not recommend it. So if you want a go-to method for your multi-objective optimization problem, I would advise you go with weighted sum or MGDA. Now, coming to the final point, which is that one should take into account that methods are converging. This is a comment in general in machine learning or any optimization method. If our methods are not converging, then we are not getting really a solution. So it could be deluded that we have a solution, but that might not be the case. And oftentimes it involves refining a lot of hyperparameters. I think that's what takes a lot of time in deep learning or machine learning in general. And this should be kept into mind. One should keep in mind about the overfitting part. So if the models are overfitting, for example, here we have overfitting in the physics laws. So we had to really find a way how to deal with this overfitting. And if your model is not converging and it's overfitting, the Pareto front you will get will also be wrong, and hence the decision you will make based on that will also be wrong. And this is one of the examples where the method has not really converged because we just stopped the training at 400 epochs. You can see that from here onwards, from orange point onwards, 0.08 to red here, they are all dominated points. If you draw a cone on any of them, you will see that they don't belong to the Pareto friend. And one might be deluded and say, okay, this is the Pareto friend, and you can I can take this point as an optimal solution, but that won't be the case. Finally, I have a simulation of a neural network where we are using the physics laws and the data laws and using the weighted sum for optimization. And this is how the Pareto front evolves if you use weighted sum. So you see that we start from a random point in some space, and then during the optimization, it finds a place on the Pareto front using the weighted sum optimization method. And then finally, it's up to the person who has to make a choice which optimal solution to take. Okay, because there are many of them, there is not a single optimal solution. Okay, summary. So we discussed introduction to multi-objective optimization problem, what it is and how it exists in nature and in deep learning. And we discussed some of the methods. There are many more methods out there. These are only few which I had discussed in my study. And we also discussed some of the difficulties which you could face while using multi-objective optimization in deep learning. And it's important that one has a theoretical understanding of the subject so that you can identify the right Pareto friend. And you should use multi-objective optimization only and only if the objectives are conflicting. Visualization is important as always. So you should be plotting them in the right scale and not go ahead with explaining that this is convex and non-convex because of this and that, but rather look at the scales at which we are plotting them in the first place. And the algorithm selection is very careful, and we should be knowing already what to expect out of the optimization method. That's where the math part becomes really important. I think one of the bigger problems in the computer science research in general is happening that the math is being thrown out of the window. I think this is dangerous because we already don't really understand much about neural networks, like what does it mean? They work, but we don't understand much why exactly. And then if we don't also care about what are these optimization methods, how do they work, what are their limitations, I think it's a little bit dangerous. And as usual, we should always care about convergence if our model is really converging. So thank you very much. This is what I wanted to discuss. I think this was maybe a lot because I had to discuss, a couple of different fields and bring them together. And I don't expect you to learn all of it in just one talk. So if you have questions, you can ask me. You can also connect to me later on if you want to know more about this field. Do we have any questions? Yeah, I can send a copy of slides. That should not be a problem. You can also visit the archive paper, which is just on the screen. The content is from that paper, which I recently put on archive, or you can simply scan the barcode. And I would be also happy to address if you have any comments about the paper itself. Let me maybe ask one question, if anybody is ready to answer. Do you already see some of the fields where you are working, where you could use multi-objective optimization? Oh, looks like nobody is thinking of using multi-objective optimization, or maybe nobody is willing to write. But in general, I would say multi-objective optimization is it pops up everywhere. Life in general is a multi-objective optimization. As I was discussing, we are always optimizing many things. Our mind is optimizing consciously or subconsciously many things, and I think it's a very interesting field. All right, so that's it from my side. If there are no more questions, I think we can close. Maybe the organizers can take over from here, and I will probably use multi-objective optimization for HWCR. I have to Google what HWCR is. Okay. Yeah, definitely. If you want to use, this is one of the fields where people have used multi-objective optimization. One of the famous papers is, I will, hopefully I'm able to find it quickly. It has around 1,000 citations. This is one of the papers. You're welcome, Akmal. And let me put, yeah.
Thank you, sir. A heartfelt thank you to Mr. Junaid Akhtar for sharing her expertise and insight with us today. We also extend our gratitude to all the participants who joined us from all over the globe. Your active engagement and thoughtful questions made this session a success. Thank you, everyone, for joining us today.
Bye-bye.
Thank you so much for the session.
Thank you.
Thank you.
Alicia and
Thank you
Abhinash.
very much.
It was really nice to be here.
Thank you.
Bye.
So we'll try to, switch on the cameras, everyone, so that we can take a picture together, a virtual picture. I would request everyone to switch on the cameras.
Yeah.
Okay, that's great. All right then. Thank you so much.